All right, we're creeping in. Yeah,
Okay.
do you want to start, Bob? And then,
Yeah, okay, so I will start off with a huge apology. In that we said about doing the calculations for inspection and testing, the sort of calculations that we might want to do prior to starting the inspection and testing process and during the inspection and testing process. And the more I got into doing this, I am showing my age. Yeah, 3rd Division Reading Elm Park, good grief. Yeah, the more we got into doing this, the more we thought, oh, hang on, this is going to take a long time. So what we're going to have to do is we're going to have to do this in 2 sections. So what I've done is I've done, this is the cable calculator, not cable, yeah, well, calculations for the inspection and testing, the dead tests. So we're going to look at like the continuity stuff and volt drop and whatever. So looking at ring circuits, radial circuits, and that sort of stuff. And what we do is we do the live cable calculations for inspection and testing. And that we'll do with things like thermal withstand and whatever. We'll do that in another webinar. Oh, another webinar I've got to write. So yeah, keep me busy, keep me out of mischief anyway. Right, okay, so we'll push on with this, and in time-honoured fashion, we're going to give you that huge lie, which is this would be 45 minutes long.
we should stop saying that.
Yeah, this is what we aim for. We aim for 45 minutes, but it never happens. But there you go. Such is life. We will see what we can do. So,
Okay.
yeah, yeah. People are beginning to know us now. Okay, so looking at cable calculations. Here we go again. Same. It's always the same. The first one always takes a little bit of a. There we go.
Wake it up.
So, first section of these, we're going to look at continuity, and the continuity calculations use the tables from Guidance Note 3 or the on-site guide, so whichever one you've got a hold of or you've got access to. And it doesn't even have to be an up-to-date one. It could be an older one if you.
Yeah, I mean, this information rarely changes, does it?
Yeah.
Now and then you get a sneaky correction factor come in.
Yeah.
But the physics doesn't change.
No, physics doesn't change. Copper conductors are copper conductors, and they've had the same sort of resistivity since the year dot. So, okay, so we're going to use the tables from Guidance Note 3 or the on-site guide. So the tables we're actually going to be looking at are table. I'm using Guidance Note 3. I use Guidance Note 3 because it's bigger and I can see it. As Dave's already mentioned, I'm getting old. Yeah.
Well, to be fair, I mean, look at the condition of my on-site guide. All right, it's immaculate. I've only had to pick up lately because I've got a couple of questions coming in on YouTube.
I'll say no more.
Yeah.
So, Guidance Note 3, I'm using tables B1, B2. Yeah, if you're using the on-site guide, it's tables R1, R2. If you're looking for them in Guidance Note 3, it's page 148. If you're looking for them in the on-site guide, it's page 196. The first table gives us resistance values for conductors at 20 degrees C. Provides for either single conductors or a combined R1, R2 value. Yeah. So at 20 degrees C, for instance, we can see, if you've got good eyesight, better than mine anyway, you can see from the table on the screen that a 2.5 line conductor with a 1.5 CPC has a combined R1, R2 value of 19.51 milliohms, and that's for every meter of cable. Okay, so if you want to know what the resistance of a length of conductor is, or a length of cable, we can use those values to actually give us a measure anyway, a value for that resistance. But that's at 20 degrees C.
I'm going to be a pain in the ass now because obviously I've got to see the presentation. So why 20 degrees C?
That's just what it is. That's just what it is on the table. And obviously, if you have an ambient temperature which is different to that, there is a correction factor which is in the next table. Okay.
So we have to have some unit to then work from. So that I mean, and this is the point. If we're working conductors, you know, the table is good, but the table doesn't apply 100% of the time, does it? We obviously have to have a measurement of an ambient temperature.
If we're up in, if it's the middle of winter and we're testing and we're on a building site and it's cold, blooming cold, we might be looking at 10 degrees or even lower when we're doing our testing, in which case we have to adjust those resistance values. If we're in the middle of summer, or if we're working in Dubai, like you and I have done, or some of the other guys have done, Abu Dhabi, out in Saudi, whatever, okay, we need to do these. Quite often they take an ambient temperature out there of 40, 45 degrees. So we have to, again, adjust the figures, because as the temperature of the conductor changes, then the resistance value will change. Okay, so these are at 20 degrees C, which is, I don't know whether they take that to be the sort of standard sort of room temperature for most people. I think I've got my central heating set on 20 degrees, so there you go.
Trying to remember now.
The thing about those tables is they will go up to a 50 mil conductor. They actually continue on the next page. At the top of page 149 is the last bit of that table, going up to a 50 mil conductor. So, we just see the bottom of that last bit of the table there. The second table, B2, gives us the factors if the temperature is different.
So the obvious thing to see here is that 20 is 1, which means no factor, no adjustment.
So no factor applies. Yeah.
You can see then how they change from 20 downward or 20 upward. Always find the one factor, then you'll know how the table behaves.
Yeah. So if we have a different testing temperature on a day, if it's not 20 degrees, then we can apply these factors, and we can then add that to our resistance tables, and then we can calculate what the resistance of our piece of conductor should be. So, for instance, if we've got a cool day, it's 10 degrees, we've got a 2.5 line with a 1.5 CPC, so your classic bit of twin and earth. The combined R1, R2 value will be 19.51. That's taken from table B1 for a 2.5 to 1.5 CPC. Multiply that by 0.96. Because it's a bit cooler, the resistance will be lower.
Right.
Yeah. So we end up with a value of 18.73 milliohms for every meter of cable, rather than 19.51.
Now, obviously, we're talking about inspection and testing here. So this is about verifying data. If we were verifying data, we'd have a design to work with. But in this scenario, if a designer had a wiring system, and that wiring system went from A to B, but on the route from A to B, it went through a variety of ambient temperatures. Maybe it went into a loft space or into a cold boiler room. Is it anticipated that we would have that data? The designer would have that data, or should we actually check? What's your opinion on that?
If we've got a large installation where there may be a number of different environments where there may be different temperatures, and they may regularly be at different temperatures, we may have one room which is cooler. So it might be a store place for food, which is kept at a cooler temperature, and the cables run through that in trunking or whatever, and then they go into another area which is warmer. Okay, then we can, if we have that data, if you have that information from the client, the customer, we can apply those factors along our cable route and say, well, okay, we've got so much of it at this temperature and so much of it at that temperature. Okay, you're getting then to really sort of nitty gritty sort of values then.
Would it be best thing to just work out maybe, I don't know, the highest temperature as the worst case and make sure that
you can work out on a worst case scenario. If you work things out in the worst case scenario and then you find, hang on, there's a problem here. If you've got other factors that apply further back down the system, which will actually reduce that issue, then you can take an engineering point of view and say, well, fair enough, I'll allow it because, 80% of the circuit is at a much lower temperature.
The problem with that, being devil's advocate, and this is why we talk about this stuff, is if we overcompensate and we assume it's a high ambient temperature and we actually install the cables in a much cooler for the majority of the circuit, technically its resistivities will go down. So full currents will go up. Right?
Yep. But then you've got the other issue, which is the classic problem we have is lofts.
Yeah.
Which in winter can be absolutely freezing, and in summer can be like a sauna. So the actual change in temperature in a loft is a ridiculous. It's the actual phenomenon there is a ridiculous thing to actually apply to our cables. It can change by. Lofts can be sort of like 60 degrees. They can be sort of 2 degrees. So there's a huge range of temperature there. and our cables are sort of sat in the middle of it. So what factor do we apply? And if we allowed, if we went really silly and allowed and went through all the calculations, allowing for that maximum temperature in the middle of summer, right, we'd end up wiring lighting circuits in 10 mil.
Well,
and this is the crazy thing.
As Paul said here, surely fault currents won't increase that much to cause a serious issue. The theory is that a lowered resistivity would create an increased fault current. And so if we installed a conductor, assuming it to be running at one temperature, but running at a much colder temperature, the science would say there's going to be a point where there is going to be a problem on that cable in a fault condition. But as Phil's just stressed, it's probably going to be a quite a significant loss or difference to determine that increased level of fault current.
Yeah.
Because there's a theory there and a science there, it's something we should be aware of when we're observing wiring systems.
But when you sort of then start thinking, well, okay, fair enough. Well, the colder temperature is going to affect my resistance, so it's going to decrease the actual resistance of the cable, which will increase the fault current. Mm-hmm. Then you've got to throw the boot on the other foot and say, okay, fair enough. But with the colder temperature, the time it's going to take for that cable to actually reach its upper limiting temperature is actually going to be longer. So when we go to look at the T equals K squared S squared over I squared, which we will do in another webinar, that time it's going to take for the cable to reach its actual limiting temperature is going to be longer because it's starting off at a lower temperature.
We mentioned that on the 7909 webinar where we said, this cable short circuit conditions will get hot, but it's outside in the wet marshland.
Yeah. It swings and roundabouts.
Yeah, and this is the point though. The textbooks, the calculations will give you information that will say, that it actually looks like it's going to be potentially dangerous. Then you've got to apply the actual common understanding on the behaviour.
Yeah, you've got to look at it from all aspects, and it swings and roundabouts. And we can drive ourselves crazy with these calculations, and in the end, we've got to take an engineering point of view and say, right, okay.
Just look at the issue of volt drop on designs. Try to be precise with that. You'll never finish.
Yeah. Okay. So anyway, we can use those tables, the actual values of resistance at 20 degrees. We can apply these correction factors if we are testing at a temperature which is not 20 degrees, and that will give us a value that we can then compare with our test result when we actually do it. And what I like to do is, before I actually start my testing on a new installation, for instance, I will do my calculations. I'll know the length of the circuit, I'll know the size of the cables, and I will actually do these calculations. So I know when I actually press my button to do my test, I've got a value that I'm expecting. Mm-hmm. And if that isn't what comes up on my tester, then I start to think, hang on, we've got an issue. Okay. So for instance, we've got, if we've got a 20 degrees C, it's at 20 degrees C, I'm keeping it simple. Using a 2.5 to 1.5, we've got 20 meters long. Okay, we've got a radial circuit feeding an immersion heater. So 20 meters of 2.5 with a 1.5 CPC, we use in the 19.51 figure. Multiply that by the 20 meters, that's 390 milliohms. So when we actually test the R1, R2 of that circuit, we do the connection at the board and we go to the end of the circuit and we do a test there. Okay, we're expecting to see 0.39. Yeah. For R1, Rn, because we've got larger conductors, the neutral is the same size as the live conductor, so we've got a 2.5 with a 2.5. So we can still use the same tables, but although it says R1, R2 there, we can ignore that and say, okay, we go with a 2.5 with a 2.5. That's our R1, Rn. We do the same calculation. This time we've got a value of 14.82 milliohms for every meter. Yeah. And then we multiply that by 20 and we come up with 296 milliohms. So, okay, fair enough. We're looking for a value of about 0.3. So when I do my tests on my circuit, my continuity test on my radial, I'm looking for an R1, R2 value of 0.39. I'm looking for an R1, Rn value of 0.3. Okay. If I don't get that, then it makes me think, makes me wonder. Remember, if we use singles cables, we may have the same size CPC. So things may change if you're using singles.
Dave's just mentioned the S squared K squared for thermal withstand. Yeah, the I squared T. That's just how you verify the final thermal withstand. We'll probably add that to the live testing one.
Well, that will be in the live testing. Yeah, I think we'll see as we run through this. We wouldn't have had time to look at live testing, not to give it proper sort of due care anyway.
So going back to that previous slide, you don't have to go back, but you've obviously got there.
I will.
You've got there 0.39, 0.30. How would you, prior to doing the work, verify the accuracy of your instrument? Would you just do a little pre-check on a known resistance? Because we have annual calibration, but we should also do supplementary pre-checks, shouldn't we?
Well, I'm checking my instrument, and this is the classic thing about keeping instrument accuracy, is when it goes off for calibration, it's only actually accurate the day of calibration. When you get your tester back from calibration, what you should be doing is actually putting it on a checkbox or a known circuit, which isn't going to change, and you should do a set of tests and take a set of values.
Yeah.
Then what you should be doing is every month, every 2 months, you should recheck your tester and maintain that data so that you fill in the same test, you fill in the values. If those values start to wander, then you need to send your tester back for recalibration. It doesn't matter whether it's 12 months, 10 months, 2 weeks, or 18 months. At the end of the day, regular testing is far more important than this business of sending a tester off for a holiday every 12 months.
But again, if you're doing the work you've just done there, if you're knowing the length is 20 meters, if you know that, and if you know the size, that is technically also verifying the accuracy of your instrument to a point.
Yes, it makes me happy.
The numbers you expect to see.
Yeah.
And that's such a good thing to think about, knowing the value you should get and actually accepting that number.
Yeah. If I get the numbers I think I should get, then it makes me happy. Okay, because it sort of bolsters my belief in my tester. I will still do these regular checks, and it's up to you how often you do them. They recommend, I think in guidance note 3 or whatever, they recommend every 2 months. What you've got to remember is that the longer you leave it between checking the accuracy of your tester, the longer it is that you've got to question all the test results you've done if it does go off of accuracy.
I was going to say something like that.
If you've left it for 2 months, you might have quite a few test sheets
you've
got to go back to. And that's the point of putting the serial number on the test sheets. That's why we do it, so we can check what was tested with that tester.
I was going to say something similar, Paul, but obviously everyone's hearing what I'm saying. So Paul says other things make me happy.
Yeah, but I'm getting old. Yeah, beer and rugby.
Mark says, what is our view on the NICIC CalCard calibration for a daily check of an MFT? So the CalCard, you're probably familiar with that. It's like a credit card size thing with it's got some inline resistors. It's like a little resistance checker.
Anything that will check that resistance, as long as it's accurate, as long as it hasn't got damaged. This is the issue with anything, isn't it? As long as the test meter, the test box, the test card, or the circuit you're testing on hasn't changed or got damaged. Because if it gets damaged, it could go slightly off, and then you're testing against it, and you're, oh yeah, this is great. I'm getting the right readings.
Yeah.
But you've got to make sure that the circuit you're testing with, or the apparatus you're testing with, is accurate.
It's an easy thing to carry around. It's a great little thing to have. Fundamentally, having it doesn't mean that your job's done. If you can use it properly and you can conclude that you're happy with your use of it and you interpret it correctly, then it's a great thing to have. Similar to just a box of resistors or something.
And another thing is, what we're like when we get together, we get our equipment out and compare it.
Yeah. Excuse me.
Test equipment.
Nice.
Oh, okay.
What are you drinking?
What sort of webinar is this? Yeah. But I do a test on a circuit. You do a test on a circuit using your meters, and if we get really similar values, we think, great, okay, that again is an indication that either our testers are both gone way off.
In that area, we have compared now and then, but that's it.
Yes, indeed. Yes, absolutely. Yes.
Right.
Okay, we'll move on. Okay, as part of that, we get what you pay for. So if you're looking to do testing, you get what you pay for. If you buy some cheap Mickey Mouse thing that just beeps, to prove continuity, it's not going to do you any good at all. Yeah. So we need to be using proper testers, that are reliable and give us proper readings. And the testers need to be maintained and they need to be kept accurate. So we need to check the accuracy regularly.
Just checking it.
When you test your circuit, compare your calculated values with the test values that you obtain. They should be approximately the same. Any significant difference would be investigated immediately. If you're doing an EIC, it needs to be checked and remedial action taken, because it's just been installed. You just installed it. If you're doing an EICR, then it will need further investigation. Right? So, because sometimes you get a read and you think, what on earth is that about? And you don't understand it. Okay, you have to put down further investigation on that one. Right? You haven't got the time to. You could spend a day looking for why. You haven't quoted for that within your EICR cost. Further investigation.
Before we leave this area, Duncan has said, if it's a 20 CPC cable, do we use the multiplier of 1.2 to the cables? You know, I believe he's coming from table B3, these multipliers here.
Not yet.
If it's incorporated or bunched in the cable. That's his
Not yet. Not yet. No, not yet. We'll cover table B3 towards the end.
Okay.
Yeah. For now, all we're looking at is a cold circuit that's not being used, not drawing any current. Yeah. Right. So for that, we're just looking at the pure conductivity.
That conductor's position between two others has no difference because there's no loading. There's nothing there right now.
Yeah. Yeah. It's a cold circuit. It's not doing anything. It's dead. All right. We're just doing testing on it. We're testing on a cold cable, which is not being used.
Mm-hmm.
Yeah. Okay. So other things to consider, though. If you consider a radial circuit, perhaps, where the conductor isn't continuous. So obviously what's happened is that you've gone off to a socket and you've cut the cable, you've gone off to another socket, you've cut the cable. So you've got a number of sections of cable which have then been joined back in terminals. There's going to be some resistance in these screw terminations, and this can add further to the test value. Now, if anybody wants to check out on page 42 of Guidance Note 3, they suggest a figure of up to 40%. Yeah, but I think they had a test value of 0.82, and they said up to 1.4 they would accept. That seems quite excessive to me to allow an extra 40% for these connections, but you know, that's what they're suggesting. I personally don't really comply with that. To me, if I've got a single outlet like an immersion heater or a cooker, so I've got a continuous piece of cable, I would be looking for a value within 10% of my calculated value. If I get within 10%, I'm happy. If I've got multi-outlets, like on radials, and I've got lots of sections of cable which are then terminated back into connections, okay, I would probably increase that to about 25%. So I take my calculated value, and because of these multiple connections and terminations, I would be okay up to about an extra 25%. If it exceeds that 25%, my old spider sense kicks in and I start wondering why. Okay, so I say, if you want, are you looking at Guidance Note 3?
Yeah, where was it?
Okay, page 42.
Of the one with the blue?
Of the one with the blue, yeah.
All right.
They talk there about the fact that I think their values are at 0.82 and 1.4, and to me that's a bit excessive.
I see 0.82 mentioned on page 43 on the next page. Okay, I'm with you. Sorry.
Yeah. So yeah, just consider if you've got multiple outlets, you're going to have some increase in the resistance. It's just the nature of the beast. Okay, and you have to allow for that. When you do a calculation, you're calculating for a length of cable. Yeah. If you don't get exactly that, don't overreact. You can always add a little bit, okay, because things change, things alter, but don't go too excessively. As I say, I'm about 25%. Anything over that, hang on, I'm not happy. Other issues with continuity tests. Okay, if you think about continuity tests, commonly suggested method, and you see this a lot in the books, and I've seen this on lots of training materials. Put a link between the earth terminal in the board and the outgoing side of the MCB or the fuse or circuit breaker, connecting the line conductor to the MET to create this test loop. Okay, you see that commonly shown. I personally am not very happy with that for a number of reasons. It's not my favorite idea. No, I'm happy sometimes. Give me a glass of Guinness and some rugby. I'm okay.
Yeah. So what's wrong with this then?
Right, not my favourite idea, and I've actually had this, yeah, on a brand new mobile unit, which you know about, yeah, because I told you about it. Brand new mobile unit that came in, all tested, all certified, all the paperwork and everything, and they'd left the link between the CPC and the earth.
Yeah.
And we plugged it in, and there was an almighty great big bang. Yeah. And we thought it was our circuit, and we reset it, and back went bang again, opened up the board.
You should probably just say we plugged it in and it went bang. We plugged it in because the site had this system where everything that was coming to site had been tested, had been checked, and that system had been in place. This had been tested, had been checked.
It was brand new.
The person checking it didn't take that link out.
Yeah, it was brand new. It came in on site with all the certification, all the documentation. What do you expect it to do? You know, you expect that the thing is all okay to plug in.
Yeah.
Plugged it in, bang. And I've also seen apprentices leave the link in when we're doing in the workshop. So hang on, I'm not happy with this way. That's just me personally. Yeah.
What's the solution then?
You live like you want to live. Well, what I tend to do is I have all my cables hanging out. And I've mentioned this a few times. When I'm installing, leave my cables hanging out, ready for doing my continuity testing at the board. The other issue with connecting into the MET is that if you take this situation here, we've got 3 circuits. We've got a cooker circuit, we've got a immersion heater circuit, we've got a boiler circuit. All the CPCs are connected into the MET. We're testing the cooker circuit. Okay, now the cooker circuit's got a gas supply. The gas is connected to the boiler. Well, the boiler has also got water connected to it. The immersion heater is also connected to the water system. The actual supply to the boiler is connected to the boiler. They've all got CPCs on them. We've actually got a whole network there of parallel paths. Now, it may not be brilliant because it's copper pipe work and all sorts of other bits and pieces. And yes, the gas is probably going to be on a rubber hose or whatever, in some circumstances. But you get the idea. We've got multiple bits of equipment which have got multiple CPCs going back to that main earth terminal, all connected. Now, when I do a test at the cooker, I'm going to include all those parallel paths. And that ignores completely any main bonding. You know, let's say we've removed the main bonding. We've still got all these CPCs, which are all providing parallel paths because they're connected to equipment which is in turn connected together through conductive pathways. Okay, so this is another reason for me not having my cables connected into the earth terminal.
What if we swapped it around? What if we went and put the link at the end of the load and measured at the board on a disconnected conductor arrangement?
Well, that's okay, but if we've got multiple outputs or multiple outlets, we've got to do that God knows how many times.
That's what the apprentice is for.
Yeah. Whereas it's much easier just to go to the board, link out between the line and the CPC at the board, and then go to your outlets on the way all the way down the circuit. To me, it's
very true. Easier. There are many illustrations of this test where they do the continuity and they put the link in the board, but they'll often have one final circuit connected to that board. They'll have a board with one final circuit, and they'll illustrate the link going from the disconnected line conductor from the MCB to the bar with the CPCs. Every time I see that illustration, I go, yeah, but in any other board in the world, there's more CPCs on that bar. And parallels are a problem.
This is why I'm always saying to guys, when you're doing installations, you're doing new stuff, you're going to then do your testing. And I again, it's one of these things. I'm of the opinion that when you install, you should test your own work. That's just me. I know some companies don't do it that way, but that's just the way I am. So it should be installed, it should then be inspected and tested, and then, and only then, should it be livened up, and we carry on to the live tests. That's how it should be. We get too many installations that are installed, turned on, the bang test, as the apprentices call it, and then sometime later, it could be the following day or the following week, you get another group of guys come in, or a couple of guys, and they come in and do the testing. It's not right. It shouldn't be turned on.
Yeah, we know the actual... we know the potential disaster that can occur where systems aren't properly tested or are put into service prematurely.
So, this is my honest, humble opinion. The best way is to have your cables hanging out install in preparation to test. And I spoke the other day about not connecting in PIRs and photocells and fans and stuff like that in bathrooms, because you're going to do insulation resistance testing. So prepare to test. And the cables at the fuse board, I don't terminate until I've done my continuity tests. That way I know.
It's moving on from this. It's a bit about IR testing. When I deliver training, I always, like the plug-in click roses you get. Yeah. Any connection like that, or it's a simple plug-in connection, is great because you can fabricate the system and then you can simply unplug to test.
Yeah.
You haven't got to dismantle, you haven't got to break it down. And if you connect your system into a plug system, even in domestics, you can get the equivalent ones. You can just simply have them all unplugged, and then you could do your testing. And there's no reason not to test. I see so many new tests done even now, where because the equipment was connected during the construction and they didn't carry the initial verification during the erection like they should, there are limbs occurring because of the obstacle of now going back and disconnecting this equipment.
Yeah.
Sensible equipment selection should avoid this.
Yeah. Okay. So this is just one little foible of mine. I like to have all the cables individually hanging out at the fuse board and do my continuity tests from there. Other issues that we have are things like if you've got cable management systems, obviously if they're PVC, it's not such a problem because they're not conductive. So PVC cable management don't provide too much problems. So quite often you'll get comparable test values, which is great. But then when you go to steel cable management systems, okay, they are going to provide you with multiple paths, because when you wire using a conduit and steel trunking system, you will have multiple connections to metal boxes, which are then connected to the trunking system, are connected to the conduit system. That's now providing with loads and loads of parallel paths and multiple pathways. Okay, so your test values are now going to be nowhere near what you've calculated. And this is just one of those things where you have to just accept the fact, okay, I've got a steel, I've got a conductive cable management system. It's going to add parallel paths. Now my test values are not going to be anywhere close to what I calculated. Yeah. The other problem with obviously steel trunking, for instance, and various other management systems, is that they can also give you false readings. Okay, so let's say, for instance, we've got a damaged line conductor. Some way down the system, there's been a damaged line conductor. It's got caught in the turnbuckle of the actual trunking. Yeah, so it's actually separated the actual cable. We're still going to get a connection there. We're still going to get a reading because we've now got this situation where the actual trunking itself, provides that loop. So we test at the outlet, and we're getting conductivity between the CPC and the line conductor, because the CPC goes back to the next socket, and it's then connected to the metalwork, the trunking and the conduit, which then is connected to the line conductor, and that provides us now with our continuity. So we're getting a false continuity reading, even though we've got a separated conductor there. And obviously that will then show up against when we do an insulation resistance test. Okay, but what it will also do, it should give us a really low continuity test. So sometimes if we get a really low continuity test, that may be an indication of a problem. If you do find that fault, because when you go into insulation resistance testing, you're going to find that fault for your very next test. And then what normally happens is that people will then remedy that fault. If it's an EIC, new installation, they'll remedy that fault, okay, because they found that there's been a problem, there's damaged cable. They'll remedy it, replace the cable or whatever, replace that section. Remember, before you go on from there, you need to go back to do your continuity test, because it may have been that fault that was giving you the continuity in the first place. So now that you've replaced that section of cable, go back, do your continuity test again, then do your insulation resistance test again. When testing line and neutral, R1, Rn, continuity tests generally performed at the end of the circuit, and we like to test Rn because it gives us proof that we've got a neutral at the end of the circuit, which means that the system's actually going to work when we turn it on. It also means that we're testing the neutral. Now, we need to test the neutral before we do an insulation resistance test. If we don't test R1, Rn, then we're not performing a continuity test on the neutral. We do an insulation resistance test. We've got a whole section of neutral that's not been connected. That could have a fault on it. When we turn the system on, half the system doesn't work because we've got a break in the neutral. And what tends to happen is people then find that break in the neutral and repair it and then turn the system back on again. And there's an almighty great big bang because the fault between the neutral and the line conductor wasn't found because it was the other side of the break in the neutral. So when we do this testing, always check your neutral conductors as well. Yeah, it's not in the book, it's not in guidance note 3, it's not in the on-site guide, but we always tell people, do a test on your neutrals, do an R1, Rn test, okay? And again, you can do your calculation and you can compare your readings at the end of the circuit. Okay, there's been a few mentions of conduit and trunking. Yeah, there are tables in some of the guidance notes and other products for resistance values of different sizes of conduit and trunking. I haven't actually gone into them here because we didn't really have enough time. The other issue with those is because you've got multiple connections into your trunking and your conduit. Again, the values are quite often all over the place, unless you're just using your conduit or trunking alone for a CPC. Yeah, then when you go to the end, yes, you can get a value, but because of the multiple connections all the way down the circuit between the conduit and the trunking and the CPCs of the circuits, all the circuits, yeah, quite often it's extremely difficult to get an accurate value. So calculation goes out the window, really.
So for people who are thinking maybe about 2396, etc., how much impact does a wiring system like that come across against their final circuit designs, in your view? Does it make much of a problem? Does it have to be included?
It makes calculation very difficult because obviously you've got these multiple pathways, and it's very difficult to assess those. Every time you connect a metal, put a CPC onto a metal box which is connected to a conduit system or a metal trunking system, you're adding in another parallel path. And you could be doing that if you've got a radial circuit going around the room. You might have multiple connections all the way down that radial circuit to that conduit system, that trunking system. And you might have 10 radial circuits in that trunking, and they've all got these parallel paths. They've all got these CPC connections. So it's extremely difficult to accurately calculate what the overall resistance values are going to be. I'm not really... Go on.
But once you've made your final decision, and it takes a while, on the number of protective conductors and the size of the wiring system, it can be done. They're just different resistivities to combine in parallel, aren't they? It's a calculation I'd like to avoid, though, to be fair.
It's a can of worms, because how many connections have you got? How many connections have you got to the trunking? Okay, and how long you've got to look at the individual circuits, how many times they're connected to the trunking and where, at what points, and how many circuits you've got in that, how that overall effect is going to be. Remember, you've got one set of trunking or one set of conduit. It's a nightmare of a calculation.
To avoid it.
It's really quite difficult, and I don't, from a practical point of view, I don't see how anybody can accurately calculate what that value should be, allowing for the multiple parallel paths within the trunking and the conduit system.
It's just
I don't see it.
It's well, from a design perspective, it's assumptions, because you're assuming you've got X trunking, then I don't know, 10, 20 other additional protective conductors, all probably connected at different positions within the trunking, making the trunking's resistance effective at different points. You're going down an avenue that you just want to, your design goes down a completely different area there.
Yeah, I mean, if you've got
it can be done.
If you've got 6 circuits, all the same, with different sizes of CPCs, you can take the resistance values of those, and you've got the conduit and the trunking, you take the resistance values of those, work out all those resistance values, and then do a calculation. You can do it that way. Will it be accurate? I don't think it will. But from a design point of view,
More of a theory,
you can do it in theory, but I'd put money on the fact that when you actually go to test it on site, the value you get from tests will be way different.
Yeah.
But yeah, it was one of those. Okay, so yes, so when we're doing the testing, we're doing continuity testing. Make sure you test your neutrals. So if we want to calculate the expected R1, R2 and the R1, Rn values for a radial circuit, supplying 4 13 amp sockets, fed on a 4mm with a 2.5 CPC, it's 30 meters long, it's in an ambient temperature of 30 degrees C. Okay, we need to get the following information. Okay, so first of all, we need to look at table B1 and we get the values for the cables. Right. So we're looking at a 4mm with a 2.5 CPC. So the R1, R2 value is 12.02 milliohms for every meter.
Mm-hmm.
The R1, Rn value is 9.22 milliohms per meter. Okay, so those are the values at 20 degrees C. We've got an ambient temperature of 30 degrees C, so we go to table B2 and we look for the correction factor. The correction factor from table B2 is 1.04 for 30 degrees C. So we've now got the values for R1, R2, we've got the values for R1, Rn in milliohms per meter, and we've got the correction factor.
Okay.
So we continue with this, working out R1, R2, well, we've got 12.02, multiply it by the correction factor, 1.04 for the increase in temperature, the ambient temperature, and then we multiply it by 30 because it's 30 meters long. And we come up with a value of 375 milliohms, which is obviously 0.38 ohms. Okay, so that's R1, R2, line and CPC. The R1, Rn, because the line and neutral conductors are the same size, is going to be that much smaller. So we've got a value of 9.22 milliohms per meter. We multiply that by 1.04 because we're testing at 30 degrees C rather than 20 degrees C. So the cable's going to be slightly warmer. Multiply it by the 30 meters, we come up with a value of 287 milliohms, which is 0.29 ohms. Okay. Now, the other thing to consider, this is a multiple outlet circuit, so there's going to be a series of connections. So we might want to allow a little bit extra, for those multiple outlets. So if we whack in the 25%, perhaps, we could probably accept readings of up to 0.48 ohms for R1, R2, and up to 0.36 ohms for the R1, Rn. Anything higher than that would raise my suspicions. If we've got fewer outlets, the fewer connections, then the less allowance we can give. Okay, so if you've got lots and lots and lots of socket outlets, then yeah, you're possibly going to have quite an increase or possible increase in the resistance value.
It's every single point of utilization is a point of potential increase in resistance, isn't it?
Yeah. Every termination, every connection point is a point of increased resistance. Okay.
Mm-hmm. And that is, by the way, I mean, your connections, whether they be, you're breaking the conductor and you're putting it into a thing which may have a slightly different resistivity. So that's, it's actually perfectly normal, isn't it?
Yeah, and people do,
as long as it makes sense with the values.
Yeah, when we're doing inspection and testing courses, you get guys that do the calculations, and then they might do a test on a.
They worry if it's not bang on, don't they?
And they worry about, oh, hang on, it's a few over, and you just think about how your system is. You've got lots of connections there. You can have that increased resistance. So
obviously, the first thing we check though with that is that they've correctly nulled, and that they've got their, if they're using like a plug and socket to go through the socket, then they've obviously made any necessary deductions. But after that, that little margin is acceptable as long as you can explain it. As long as you can explain it.
Yeah, plug-in leads. The plug-in socket type test lead is so useful and it saves you so much time. but we've got to be aware of the fact that sometimes it can give us a very poor contact.
Yeah.
And there's many a time where I've been actually putting sideways twisting pressure on a plug on a test lead, trying to get a good contact on a circuit, on a socket. And the other thing is the actual switch on the socket.
Yeah.
You know,
That's
yourself,
the
you
thing.
can switch that switch over multiple times and it will change the reading all the time.
But that's the thing with the low resistance ohm meter, and that's why it's great with those courses, because you can get the guys to just really understand how accurate and how much movement there can be in the values with a simple twist of the socket, you know, or you know, take it, you know, a couple of insertions just to kind of attack any dirt in there.
Yeah, I've had readings on test rigs of over like 1.4, 1.5 ohms, you know, and then you flick the switch a few times and it comes down to about 0.29. And you think, well, you know, and that's just the nature of the beast. And the thing is, the older sockets get, the more likely that is to happen. But it'll also happen on new sockets, brand new stuff out the box. So
it does, yeah.
So if we got an unexpectedly high reading, we should investigate it. If we're carrying out an EIC, it's new work, just put it in. We need to sort out why we've got an unexpectedly high reading, and we need to remedy that. If we're doing a periodic, we're doing an EICR, then if we've got an unexpectedly high reading, then it's an FI at least. Yeah. Taking measurements, if we've got a circuit with multiple sockets on it, a radial circuit this is, then taking measurements back through the circuit could help to identify any loose or any problems. Okay, again, calculating the values helps. Okay, so in the last exercise, we had the 4 sockets. If they were evenly spaced from the board, yeah, so 30 meters in total. So the first socket is 7.5 meters, the second socket is 15 meters, and so on. Yeah, and we had values like we've got at the bottom. Yeah, you'd look at that and you think, well, which one is going to most likely have the problem at it? Okay, so you come from the fuse board, the first socket you get to is 0.47.
And you're saying that's the same distance from that one to the 0.5?
They're all equidistant. All equidistant.
Okay.
So the first socket is 7.5 meters from the board, the second socket is 7.5 meters from the first socket.
We're going up 0.11 ohms from 58 to 69, from 69 to 80, aren't we?
Yeah, yeah. So you know, you look at that and straight away common sense tells you that the problem is going to be at that first socket.
That first leg.
Yeah. The first leg is where the issue is.
Yeah.
So you can use these calculations to actually indicate and help you with fault finding. Yeah. Okay, so that's radial circuits. We're now going to go on to rings. Okay, ring final circuit. When we're testing rings, what we're looking at is obviously, because it's a ring, or the common sort of method of wiring up rings is to use a 2.5 conductor with a 1.5 CPC. We wire it as a ring, so we go out, we go back, okay, and then we protect it with a 32 amp circuit breaker or a 30 amp fuse. We know that that isn't, the actual 2.5 isn't capable of carrying that level of current as an individual conductor, and that is why it's important that it is a proper complete ring, so that the current is actually shared across the legs of the ring. And it'll only do that if they're the same cross-sectional area, they're the same material, so copper, and roughly the same length. All right, so when we go out to feed a ring, we don't go in, out, in, out, in, out, and then take the last leg all the way to the end. Right, we try to stagger them to try and keep the lengths as much as possible the same. If we do that, then they will carry current pretty much equally down each leg of the ring. Okay, thereby we can protect it with a 32 amp circuit breaker. Jobs are good. So what we're looking for when we do a ring is make sure, first of all, that the legs, the individual legs, are properly continuous. Yeah, they do actually form a ring, and effectively also what we also want to prove is there's no interconnections within the ring, loops within the ring. And this happens sometimes when somebody puts an additional socket in, and then they put another socket in, and then they think, actually, I can get back to that socket over there and make this part of the ring. We end up with a ring within a ring. What will happen then, obviously, is that the current demand will be different on different legs of the ring. So that can lead to part of the ring, certain cables being overloaded. Using the same tables, we can calculate the end-to-end readings, the R1, the Rn, and the R2. This is little r1, little rn, little r2. And these actually go in the actual form. They go on our test sheet. There's actually a box for them. Okay, so if we've got a ring which is 44 meters long, for instance, in other words, 22 meters to the furthest socket, it's wired in a 2.5 and a 1.5 CPC. Okay, again using the tables, and this time we're not worrying about temperature. I've done it at 20 degrees C. Yeah. For the R1, yeah, the resistance of the line conductor, we're going to use 7.41 from table B1. That's for a 2.5 conductor on its own. We're going to multiply that by 44 because it's 44 meters long. We'd be looking to get a value of about 0.32 or 326 milliohms, so about 0.33 ohms. Rn, exactly the same size conductor, so exactly the same value. Okay, so again, we're looking for 0.33. Little r2, we're going to use a 1.5 CPC. The value from table B1 is 12.1 milliohms per meter for that cable. We multiply that by 44. We come up with a value of 532 milliohms. So let's call it 0.53. And then we do our tests, and we can see from our test meters that we've got 0.33 for the line conductor, we got 0.33 for the neutral conductor, and we got 0.58 for the CPC. Okay, that's fine. Yeah. Remember, there could be connections and stuff like that, so 0.58 is well within what we're expecting. Then we talked guidance note 3 and the on-site guide and various other publications say to us, well, we can use this comparison factor of 1.67 because the CPC is smaller than the line conductors in a twin and earth, so it'll have a higher resistance. We can use this comparison factor 1.67. The value of the CPC will be roughly 1.67 times the value of the live conductor. And that only works obviously if the CPC is smaller, so it won't work for singles cable. Yeah. For twin and earth, we can use that. So if we look at 0.33, if we multiply that by 1.67, we get a value of 0.55. Yeah, that works out about right. We did a calculated value of 0.53. We've got a tested value there, 0.58. So it all seems to be working out no problem. Again, we have to consider things like metal containment systems. Yeah, metal trunking, metal conduit, they're going to send these values all over the place. Yeah, so we're not going to get these comparative values. We're not going to get these test values when we're dealing with metal containment systems. The other thing is that quite commonly, if we're using a metal containment system, the CPC will be the same size as the live conductors. So again, the values are going to be different. We're not going to use this 1.67 factor, and we need to use the 2.5 value rather than 1.5. The second step of the testing requires us to cross-connect the line and the neutral at the fuse board, in to out, out to in, as we say, and then test at each outlet around the circuit, obtaining an R1 Rn value. The value should be approximately a quarter of the R1 plus Rn value, because when we connect it as a loop like so, we are effectively doubling the cross-sectional area, which will halve the resistance, and we are halving the distance, the length, which again will halve the resistance. So a half of a half is a quarter. So if we take the values of the end-to-end loops of line and neutral and add them together, what we should be reading is about a quarter of that value when we do this test. So here we've got R1 Rn, add it together, 0.3, 0.33, add them together, divide it by 4, we should be getting a test value of 0.16. So again, you do these calculations before you do your tests. So when you press that button, you're looking for a value of 0.16. If it's much different from that, then the alarm bells start to ring, okay, and you can take further action. If it's new stuff, remedial action. If it's an EICR, could be FI. We can also take a test at the board. Okay, because we're going to get exactly the same value from there if we do a test from the board of the conductors as shown there in the diagram. So you can test at the board, but also test at all the socket outlets. It's part of the polarity test, so it's important that you do that. One of the issues with this test is the fact that if you look on your test sheets, the scheduler test results, there isn't normally a box for an R1 RN test value. And so what we do find is that some people skip this test because, oh, we don't need it. There's no box for it. Yeah, it's a very important test. It needs to be done, and we need to make sure that we record that. Okay, if necessary, put it in the comments column. The other issue with this test is, yeah, if you've got twin and earth cables, it's easy. You know which pairs go together. With singles cable, it's not so easy, especially if they've all been mixed together and not been identified, not been labeled. Which is the in, which is the out. What I say to people is that it doesn't matter. Just grab a set of cables, connect them together, in to out to in, whatever you think it is, and start testing. If you've got the connections wrong, you'll know fairly quickly because the sockets nearest to the fuse board will give you a really, really, really low result. And as you move away from the fuse board to the middle of the circuit, those results will get bigger and bigger and bigger. Yeah? If you find that the results are differing in that fashion, tiny at the beginning and then increasing as you go towards the middle, you know you've got the connection wrong. Just go back to the board, swap your connections over, start again. All your results should be roughly the same as you go around the circuit. If the sockets are on a ring and they're part of the ring, all of those results should be exactly that, well, pretty much the same. Okay, and they should be roughly little r1 plus little rn divided by 4. Now, of course, that doesn't work if your socket is on a spur off of the ring because you've got an additional piece of cable, and we'll cover that in a bit later. The third step is to cross-connect your line and CPC, and again, we can do the same calculation. Okay, we've got little r1 and the little r2 value. There's a typo there. Should be little r1, little r2. Add those together, divided by 4, we've got a value of 0.22. So when we do the test at each socket outlet, we should get a value of 0.22 for the R1, R2. Okay. Again, any parallel paths from containment or equipment which is connected or bonding would affect these results. So if we take a ring finder circuit, let's do an example here. We've got a ring finder circuit using the same tables. We've got a ring which is 80 meters long. So it's 40 meters to the furthest socket. It's wired in 2.5, 1.5, believe it or not. Twin and CPC cable. Let's work out what the values should be. Okay, so from our book, if it's a 2.5, our little r1, we take a value of 7.41. We haven't been given anything about temperature, so we're just going to use that straightforward value. We've got 7.41, and we're going to multiply it by 80 meters. Yeah, and we should come up with a figure of about 592 milliohms. So round it up to about 0.59 ohms. Rn will be the same. It's the same size conductor. If we now want to calculate little r2, we would take the value from the table. It's a 1.5 CPC. We take 12.1. We multiply it by the 80 meters. 40 meters there, 40 meters back. So the total ring is 80 meters. 12.1 times 80. And we come up with a value of 968 milliohms. So about 0.97. Use the comparison factor. Compare the values. Well, little r1, 0.59. Multiply that by 1.67. Comes out at 0.98. So yes, the comparison factor indicates that we've got the right sort of figure. Little r2, when we measured it, was 0.97. So that looks okay. If we now want to calculate the big R1, big R2, and the big R1, big Rn values for the same ring, R1, Rn, we take the 0.59 and the 0.59, add them together, divide them by 4. That's the live conductor and the neutral conductor. Little r1, little rn figures, add them together, divide by 4. And we should have a value of about 0.3 ohms. We do the same with the R1, R2 value. Little r1 was 0.59, little r2 was 0.97. Okay, add them together and we divide by 4, 0.39. So those are the sorts of values we should be getting. So have a look at the following table. We've got a table here with some test results from 5 socket outlets. These were obtained on a ring finder circuit from 5 sockets connected. The circuit was wired in 2.5 with 1.5 CPC, twin and earth cable. The distance to the furthest socket was 25 meters. The ambient temperature was 10 degrees, so it was cooler. Okay. And these were the actual measurements we recorded at the socket outlets for R1RN and R1R2. So what do these values tell us? Well, the first thing we need to do is work out what the values should have been. So we start by working out what the little r1, the little r2, and the little rn figures should have been. So if it's 25 meters to the furthest socket, okay, we can calculate it's 10 degrees. So if you look at our table, table B2, it tells us to apply a factor of 0.96. It's colder, so a lower resistance. So we got 2.5, which is 7.41. Multiply that by the 0.96. Multiply that by the 50 meters. We should have a little r1 value of about 0.36. Little rn will obviously be the same. Little r2, because it's 1.5, we'll have a value of 12.1. Multiply that by the factor for temperature, because we've got a colder testing temperature, 10 degrees. So we apply 0.96 and then multiply it by the 50 meters. The little r2 value should have been 0.58. So we've now got our R1, our Rn, and our R2 values. We can now calculate the R1 plus Rn and the R1 plus R2. R1 plus Rn, well, we've got 0.36 and 0.36. If we add them together, it's 0.72. So R1 Rn, divide that by 4, 0.18. So the value of R1 Rn should have been 0.18. If we do the same with R1 R2, we've got 0.36 and 0.58. Add those together, divide it by 4. We've got an R1 R2 value of 0.24. So not allowing for any discrepancy for terminations and stuff like that. Okay, the values we're looking for is R1 Rn 0.18, R1 R2 0.24. So if you look along those sockets, well, so socket 3 looks about right, allowing for that a little extra because we've got 5 sockets here all connected together in a ring. So we've got a number of terminations there which might have had a little bit of resistance. Okay, so socket 3 looks about right. So what do we think about socket 4? Any verdict on socket 4? we got an R1RN reading 0.2. Well, that seems to be about right. What about R1, R2? Got nothing there. And there's a few correct answers coming in here. Yeah, this is the classic sign of reverse polarity. When you test between line and neutral, you get a reading. Well, it doesn't matter which way around line and neutral are, you're still going to get a reading. So if they're round the wrong way, yeah, then you'll still get that reading. But when you test from what you expect to be the CPC and line, you're actually testing between the CPC and neutral, so you don't get a reading. So that is the classic sign of reverse polarity. When you get an R1RN value, but you don't get an R1, R2 value. Yeah, that's a classic reverse polarity. Could be something else. It could be some connection come loose or whatever, but it's the classic sign of reverse polarity. So you need to drop that socket and have a look inside there. Yeah. What about, let's have a look at, well, number 2, socket 2. Socket 2, instead of about 0.21, which we got on socket 3, we got 0.29, so it's a bit higher. Instead of 0.27, we've got 0.34. Well, they're both higher. Both values are higher. Not hugely high, but a bit higher than what we expected to be on the ring. So what can happen if we get a little bit increase on both readings? Well, yeah, there we go. Yeah, it could be a spur. And that actually equates to a spur off of that ring for about 5 meters of cable. So we got a slightly higher reading on both. Not hugely high, but slightly increased. And that's a classic sign of a spur. Could be other things, could be poor connections and stuff like that, but it's a classic sign of a spur. Okay. Okay, so that leaves socket 1 and socket 5. Okay, so have a look at those. Socket 1, we got readings that are way over the top on both R1RN and R1R2. They're way over the top. Very unlikely to be a spur unless you've installed a spur 3 doors down. And socket 5, we've got a R1R2 looks okay, but R1RN is high. So what could be the issues there? Okay, so we've correctly identified that socket 3 was about right. Socket 4, reverse polarity. Socket 2, probably a spur off of the ring. As I say, it's about 5 meters of 2.5, 1.5. Socket 5 could be indicating a loose neutral. And maybe the neutral conductors are still touching, but the connection is loose. They might still be making connection. They still might be touching, which gave you your little RN. It gives you all the other readings okay, but doesn't give you a good connection to the actual socket. Okay, so it could be a loose neutral. Or it could be poor contact on the neutral of the socket. And we've already said about the switches, they can be really dodgy. The actual pins going into the socket, if you're using a test plug, they can sometimes not make a very good connection. Yeah, especially when if the socket's been in a while, it loses its sort of springability. Yeah. So yeah, it could be a loose neutral where the conductors are still touching, but not making effective contact with the socket, or it could be a poor connection within the socket on that neutral. But there's a definite issue there with that neutral. Socket 1 suggests a number of things. It could be the switch on the socket is naff, and we do get it. We do get it sometimes where the switch is completely no good, and you sit there switching it backwards and forwards, and it's going all over the place. It could be contact with the socket again. Okay, when you plug in, it's not making effective contact inside the socket. If it's on the line conductor, it will affect both of those readings. Yeah, because we've got line neutral, we've got line CPC. So if it's on the line side of that, it could be affecting both of those readings. Yeah. So it could be, as I say, poor contact with the plug itself. One way of sort of looking at that is wriggling the plug around. putting some sideways pressure on it, almost twist it, try and twist it and put some sideways pressure on it, sometimes you will see the reading change. Now, the trouble with that is, of course, is that you might get you might end up getting a reasonable test reading eventually, but what's going to happen when people actually plug equipment in there? Is it going to make effective contact? So if you do come across a socket which is giving you problems like that, you might be better off to change it. Okay, because when you've walked away and that's livened up and you've left the installation and the person there is using it, they're going to plug in and they're going to expect the thing to work properly. If we've got poor connections there, we could get overheating. Another good thing about R1RN readings, we talk about taking the R1RN readings and calculating the R1RN readings, is that we can use that for volt drop calculations, which can be very useful. We need to determine volt drop, and we do it by calculation. We don't go and measure the voltage at the end of the circuit. It's always a calculation. Table B3, this is the third table in the guidance note, provides factors to be applied to the resistance values in table B1, for the cables at 20 degrees. And this is because when we're looking at volt drop, we're looking at a circuit which is drawing current. Volt drop will change. The more current you draw through the circuit, the more voltage you will drop. It's Ohm's law, V equals I times R. It's the current multiplied by the resistance. The more current that goes through, then the volt drop will increase. Okay. Also remember that as the current goes through, the temperature of the cable will change. So when we're looking at volt drop calculations, we need to consider and factor in the temperature of the cable at its maximum operating temperature under use. So when we look at table B3, it's talking about a 70 degree C thermoplastic PVC. So for twin and earth, we would use that column there. Now, obviously with a twin and earth, it's incorporated in a cable or bunched. So we would use a factor of 1.2. Right, and this is for, as I say, volt drop calculation, because we've got to consider that the circuit is now under use and it's now at its optimum or maximum operating temperature under normal use. So when we're looking at doing these calculations, we can get our R1RN value. We can calculate the expected volt drop. So for instance, for a 13 amp immersion heater fed by a 1.5 twin and CPC cable, 20 meters long, we can calculate the actual resistance to the cable from the tables. We've got 14.82, that's the line neutral resistance. R1RN, multiply it by the 20 meters, that gives us a value of 296 milliohms, about 0.3 ohms. Then from table B3, we apply that factor for the increase in temperature for the circuit when it is under use, looking at the maximum operating temperature. So we use the 1.2 factor, we apply that. So when we're looking at the total volt drop, to calculate the total volt drop, it's the 13 amps, the current, multiplied by the resistance to the cable. The resistance to the cable is going to be 0.3, the R1RN value from table B1, multiplied by the correction factor of 1.2 from table B3. And we multiply that all through and we get a volt drop of 4.68 volts for that circuit. Remember, with volt drop, we're looking at 3% for lighting, 5% for all other circuits. If it's off a public supply, a DNO, if you've got your own private supply, you can increase both of those by 3%. Happy days. So we're looking at, for lighting circuits, we're looking at a maximum of 6.9 volts. We're looking at 11.5 volts for every other circuit. So this value of volt drop, 4.68 volts, is well within both of those. So happy days, we're well in. Now that's obviously just for the final circuit. What we have to consider when we're doing volt drop calculations is we've got to consider distribution circuits as well. So as well as the final circuit, if we've got distribution circuits feeding a distribution box from a supply further back at the origin, we need to add in and factor in the volt drop on the distribution cable. as well as the volt drop on our final circuit. Once we've done the calculation for the final circuit, we go back and look at the distribution cable. We work out the volt drop on that, and that again is dependent on the cross-sectional area and the current being drawn and any other factors that apply. Work out the volt drop on that cable, and then add the volt drop for that cable to the volt drop for our final circuit cable, and that is the total volt drop for that circuit. When we're talking about volt drop, we have to calculate it from the origin of the installation. Yeah, not just the final circuit. It's got to be from the origin. And those 3% and 5% factors apply from the origin. So 6.9 volts, 11.5 volts. Okay, so that is it. I did say we would never get onto live testing, and I was proved correct. You're still awake?
Yeah. I mean, I've been maintaining some leads and stuff. It's 4:25.
Yeah.
Okay.
Yeah.
There's a couple of questions there and 104 messages there. So yeah. Right.
It's one of those. I knew it wasn't going to be. I knew we were never going to fit all of that into one session, which is why I said we have to do cable calculations for live testing on another day.
Okay. Right.
And we'll advertise that.
Okay. Let's let me just go to the Q&A, and then I'm going to scan down the chat. So Paul says, very interesting, David's question. I don't know which question that was specifically. There was a question from David. How do you test a hybrid ring theory lollipop ring having a 6mm T&E going to a ring of sockets in 2.5mm? So you're familiar with the hybrid ring?
No.
Yeah, basically imagine you've got a ring.
Yes. And
you've moved the board, and let's say you've got two 2.5s going to the board, but you don't want to move those 2.5s to the new board position. So instead you you connect them maybe to a 6mm or 4mm or something, and then
right,
in that cable to the board.
Yeah.
So that's the hybrid. So you've got that. So you haven't got end to end at the board. You've got a cable there that feeds a bit where it splits.
Right. Well, in which case, what I would do is I would test where it makes the connection to the hybrid connection, if we call it that.
Mm-hmm.
I would do a normal ring final circuit test at that point. Yeah. Then I'd do a radial test on the cable going back to the board, and I would add the values together.
So you'd have an R1, R2 of the radial part of the hybrid connection.
Yeah.
And you have the R1, R2 of the ring itself, and you'd have those two R1, R2s.
Yeah. Because you still need to prove that ring part as a ring.
Yeah.
Yeah. Because obviously the current carrying capacity of the cables and the overcurrent protecting device. So you still need to prove that as a ring. But then when you're working out your total values of R1, R2, R1, Rn, and so forth, you would have to add in both sections of it.
Yeah. Okay. Because in principle, it still have the same overcurrent protected device. We need to make sure there are no loops within that loop.
Yeah.
Okay. Daniel said, how would the 1.2 multiplier be appropriate or accurate if they are being tested at lower ambient temperatures? So if we're thinking about the 1.2 multiplier and we're testing at lower temperatures, so the multiplier isn't actually in effect. Right.
The 1.2 multiplier is effectively down to the current running through the cable. Yeah. Mm-hmm. So when you look at guidance note 3, it says when you've got doing the volt drop calculations, only for volt drop calculation, you use that 1.2 because you're looking at a circuit under use. Yeah. Mm-hmm. And it says apply it to the values in table B1. So you've got to apply it to those 20-degree values. Mm-hmm. Now, what it also says is if you are of the opinion that you're not actually going to use the circuit at its full rating, yeah, or if you are of the opinion that other temperatures may have a factor, you can make adjustments. Now you've got to make those adjustments yourself. You've got to decide what adjustments you can make to those factors, and it doesn't give any other information apart from that. So if you know that you're operating in a low temperature, you may want to say to yourself, "Oh, hang on, this is going to affect it." There is actually a factor of 0.004 per degree C. That's a resistance value. Every degree C that your cable temperature increases or decreases, it affects your resistance by 0.004 ohms. Mm-hmm. So you can, if you want to, you can use that factor and sort of work it back and say, well, okay, that's the resistance values of this, but my temperature here is that much lower, so perhaps I can adjust that using that factor. But again, there's no other information apart from that, and it basically says use your own skill, judgment, and guidance.
Okie dokie. Okay, Colin says, how can you calculate the length of an existing circuit?
Yeah, but yes, this is one of those, isn't it? You can't. It's basically, I'll tell you what I do. I just pace them out roughly. At the end of the day, if I'm within a few meters, that's fine with me.
Yeah.
But once you know where the circuit runs, or you can guess where the circuit runs, and this again is one of those things where you have to use your own skill judgment. But you might think it runs a certain way, but they might have installed it a different way. So you can be out.
We'll have books like this, though, where it's calculated, maximum lengths, etc., and it's just transposition.
Yeah.
Assuming we had the R1, R2, and the R1, R2 was actually correct with no parallel paths or anything compromising the value, and the value was an accurate representation of R1 plus R2, you could then technically transpose the R1, R2 calculation formula. So if R1, R plus R2 is milliohms per meter times length over 1,000, so that would become length is equal to your R1, R2 over the milliohms, divide and then multiply that by 1,000, and that would give you a calculation of the length from the R1, R2, but your R1, R2 may not be purely representative of the cable's resistance itself.
You might have some
parallels,
slightly loose connections in there. You might have parallel paths. The problem working backwards is you don't know what other factors there are in the circuit.
But because people think they're clever and they can play with maths and algebra, they'll put page after page after page of calculations in these books saying that we can do that. Yeah.
I would just say one thing to all of that is that all these calculations and facts and figures and formulas
are very impressive. They sell books.
Fantastically impressive.
They sell books.
Nothing is better than common sense and an experienced electrician who knows how electrical systems are put in
look at the index
and worked,
of the design guide for
and use your own skill and judgment, because some of these calculations you can pretty much throw out the window sometimes if you use your own skill and judgment and you know how the electrical installation has been put in.
Common sense is not in the index of the design guide.
No, it's not in there. No, it's not in definitions either.
Oh, well. Okay. Yeah, but the way the books do it, or the way people say, "Oh, you can calculate that," it's just algebra transposition of the formula. That's all that is. Yeah. But as Phil said, there are many reasons why that won't be accurate. Okay. All right. Ben have you put that in the chat as well, Ben? There's an article about calculation of hybrid final circuits. I should anticipate the information similar to what we've said. There's an NIC article about hybrid circuits. Okay. If they said anything different, I disagree with them.
All right.
I'm going to scan through the chat now. Yeah, okay. So David mentioned S squared. We'll cover that in the thermal.
In the live testing bit.
We covered the cal cards. All right. Are all copper cables the same? Can poor imported cables have higher resistances due to impurities in the copper?
Yes.
This comes back to the idea of getting reputable suppliers, really. But yes.
Do you remember the training cable fiasco?
Yeah. It was.
There was a cheap rubbish cable which it had a red stripe down it. It was cheap as chips, and it wasn't copper. It was a mixture of metals.
You sneezed on it, it'd break.
And it was basically produced for training centres to give us high resistance values on small test rigs.
But we weren't allowed to liven them up, which meant we couldn't do IR tests.
No.
So they only had one function, which was really to practice cable installation skills, but you couldn't really do much. And the continuity values were always, if your books say R1 plus R2 equals this relative to the length, use that cable. No. Yeah. But that stuff should not be in the field. But yeah,
it got onto the open market, didn't it? It got onto the open market, and people were using it to install into houses and stuff. And there was a big furore about it. Yeah.
Okay, Kevin says you'll need to ensure your tester is at the same ambient temperature as the circuit under test. Taking your MFT from a cold van to a warm house could give you a 20% difference. Yeah, it's true. I mean, I've actually seen this where I've got early morning cold instrument. And I see as I start using it, the values start to move.
Mm-hmm.
There's a lot. Yeah, it's a good point.
The more tests you take, the values
And
change.
manufacturers will say that. They'll say, give it time to cool down, because obviously as we pass those currents through, it heats up. And if we carry loop after loop after loop after loop, or constantly carry IR tests, they're going to get warmer and they're going to start having off accuracy.
I think we should build into the testing procedure, into the testing program, that you get there in the morning, you get your stuff out the van, and then you have to have a cup of tea and several chocolate biscuits before you even start. And that allows your tester to actually warm up, and we should be allowing for that in the cost as well.
Yeah. Kevin says he's got one of the new Martindale Proof units which has a built-in cal checker. I don't think mine does. I've just been testing some of my stuff ready for tomorrow, but this doesn't have an inbuilt checker, I don't think. No. I'll probably get some new stuff anyway. Parallel paths, listening sales, bang bang. What if the CPC is conjure tracking? I think you came on to that with the parallels. Yeah. We can. This is the thing with this. We can go to town on this subject, and we could probably spend the best part of 3 or 4 hours giving examples, giving information, and playing with the data. It would help understand it, but it would also wind you the hell up. So,
there is a point where you get to overcalculation, and the thing about all this is to keep the calculation process simple, and understand when the calculation process is not going to work. Very good bit of advice for 2396 people. You know, I mean, you can go to town. I was guilty of doing that, and just simplify the design a little bit to not have to do it. Okay, mentions of JWs. He's done. I don't know if that's regards to resistivity of steel or if that's regards to continuity, but if anyone says anything about JW, I can't stress anymore how great his content is. Yeah, he's got some great stuff out there. So always worth watching. I don't know. I was on Skype with him just the other night. He's cracking on with more content, which is awesome. Okay, James says, I have conflicting opinions on this from lecturers. Confused the hell out of me. I don't know as to when you said that, but I'm not surprised. I think it might have been to do with the trunking and conduit system. I'm absolutely not surprised. I was at a Sparks thing not long ago in a room full of trainers. Some of them recognized me, some of them didn't, and I was kind of like just talking to there's a chat from Mega talk about electrode testing, and they were just so disconnected from it. You know, there are some great trainers out there. I have to say. I know many, but there are many that they're just not doing enough. Okay, let's get on because we really should finish this. Flicking the switch load drops the resistance. Switching the that's on sockets. Flicking the switch loads drop the resistances. Contact resistances. If you've got things that have not been operated for a long time, you've got new switch gear from the wholesaler, but we still need to verify this. This again goes to the point of the initial verification, and that key word, which we don't cover enough, is functionality. I mean, we've done it in the previous webinar. We said, there's a functionality box for our CDs and AFTDs. But what about everything else which requires, verification of function, especially on initial verification where it's fresh out the box? I've had MCBs fail. I've had sockets fail. And unfortunately, sometimes you've tested, you do that check after you've just installed it. With MCBs, for example, I had one sent to me, and it was on a Saturday job, and I couldn't get it replaced. So now when I'm in a wholesaler, I take delivery, I will do checks, just simple continuity checks to verify the contact resistances are there. Do what you can. But functionality is key. Okay. I think James is talking about the parallel paths, whether or not you keep parallel paths when you're testing. Yeah. Quite often, it's almost impossible to get rid of them. To be honest. Well, you've got to finish at some time, haven't you? To get meaningful test results from your calculations, then you want to eliminate the parallel paths. If you can do that so that you can double check your test values against calculations, fantastic. But remember, obviously, that when the installation is under use, all those parallel paths are going to be there, which is quite often why we tend to get rid of as many as we can when we're doing the dead testing, and we just want to get the proper continuity values. All right, and then we put them back in for livening up and doing live testing, because under live situations, obviously all those parallel paths are going to be there. They will have an effect on earth loop impedances. They will have an effect on fault currents, and we want to know what those effects are. So yeah, it's for dead tests, we want to try and eliminate them so that the calculation values mean something. For live testing, we need to have them in there so we know how the installation is going to react, as installed.
It's
a case of
both scenarios.
Yeah, it's a case of using your electrical knowledge and know-how and think, hang on, how is this going to work? Oh yeah, I really need to have that.
It is one of the problems, because I remember when I was doing testing and I started getting experience with it, I started to think about how I could do the work as holistically as possible, where I'm trying to capture as much as I can at that one point instead of having to do it again. And I've seen people say, oh, you can obtain prospective earth fault current from your ZE value. You can't take the calculated PEFC from a measured ZE because of the complete concept you've just explained about the parallel there.
You won't have any bonding connected or anything.
Oh, so and that is, sometimes we try to rush things, we try to simplify things too much. We need to kind of take a step back. Sean arrived late. I don't know where you were, Sean. Where have you been? Don't worry, this will be uploaded, and we're going to carry this one on at a later date, buddy. Then Kevin said we were only on slide 3. Cheeky. But yeah, we were far in.
Okay.
All right, the other part of coding. Yeah, I agree. All right, let's get to the bottom. Is there a bottom? Crikey. Live. All right, these guys are answering your questions for your sockets, which is good. Bad connections, loose R1R2.
No, Dave.
Is the Ninja building a DeLorean? No, I am not building a DeLorean, buddy. I am. What was I doing? I was trying to fix this damn thing. Little 3-phase motor I've got running on single phase at the moment. Gonna get
as you do.
Well, what do you do in your spare time? Just getting that ready. Okay, look. Let's get to the end.
Let's call it a day.
There must be an end. There must be a bottom.
There is.
Here. Where is it? Right, the hybrid theory is allowed. Yeah. Oh God, is there a bottom? All right, yeah. Thank you, Ben. He's pasted the article there on the. That's where I'm at, guys. This is where he's pasted this article. That's 10 minutes ago. Crikey. All right. Can you guys just leave so I can find the bottom of chat? Okay. Looking forward to 2 philosophies. Yeah, we're going to have some good discussions on that and decide what action to take. Thank you, everyone.
There's a lot of thank yous.
Thank you. Yeah. All right. Right, I'm going to stop reading them now and assuming that everyone's happy. Look, yeah, we'll resume the code one. We'll crack on with some more of that in a couple of days. We'll do something. And then we're going to have to resume this one.
Ladies and gents, thank you very much for your participation. And look after yourselves.
Yeah, and I will. Oh, cheers, Ben, for the cal check. I'll check that out. All right. Peace. Bye-bye.